Welcome back, students. In this chapter, we'll begin our discussion of chemical kinetics, which is the discussion of rates of reactions. The author of our text introduces this topic by talking about how lizards are ectotherms. In other words, they're cold-blooded creatures whose body temperature matches the environment's temperature, and when the temperature of their bodies drops, the reactions inside their bodies slow down. And in this way, the animals actually move slower when they're cold. So the author discusses how, when his children were little, they would take ice water and go outside and throw the ice water on the lizards, which allowed them to catch the lizards because the lizards' metabolic processes slowed down when they became cold, and thus when the children threw ice water on them. Now, certainly, I wouldn't advocate lizard cruelty here. It's just an example of how chemical processes are often dependent on temperature. In this chapter, we'll see how different factors affect the rates of chemical reactions, things such as temperature and concentration, and that'll help us understand the topic of chemical kinetics. Chemical kinetics is the speed of a chemical reaction. It's also called its reaction rate. The rate of a reaction is a measure of how fast the reaction makes products or uses up reactants. The ability to control the speed of a reaction is important, especially if you'll be something like a chemical engineer. You'll need to make sure that the reactions your company is performing are economically feasible by being fast enough, but also that they're viable, that you can control them, and that they don't become out of hand and cause something like an explosion or a boilover. Rate is how much a quantity changes in a given period of time. You may have used a term such as miles per hour or kilometers per hour when talking about how fast your car is moving. We use similar terms when we're talking about chemical reactions. We define chemical reactions in terms of the change of the quantity of reactant or product in a given period of time. We usually define the rate of a chemical reaction in terms of how much the concentration of a reactant decreases or a product increases in a given period of time. For reactants, we would put a negative sign in front of this definition. So, for example, if we're considering the reaction H2 plus I2 forms 2HI, if we want to define the rate in terms of the reactant H2, we know that if this reaction is moving in the forward direction, we'll be losing H2 over time. So we put a negative sign in front of the concentration of H2, and we define that as change in concentration of H2 over change in time, or delta H2 over delta time. And change in something is defined as final minus initial. So here we have the concentration of H2 at T2 minus the concentration of H2 at T1 over T2 minus T1. So the change in concentration per unit time. Here we have a more visual example. We see here two different reactions. The reaction on top has a faster rate. Here we have A plus B forming product C, and the A is represented as a blue pill, the B as a red pill, and the product as a green pill. We see that as the time changes, the green pill or the product begins to increase, and finally, after 45 minutes, we see that we have only product formed, or only product left. In the bottom example, we have a yellow plus blue pills forming a pink pill. When we begin, we have only starting materials. Over time, just as above, we begin to form product. But in the end, after 45 minutes, we still have some starting materials left. This is demonstrating that some reactions occur faster than other reactions, and that's why we need to define rate. We need to be able to determine how fast our reaction is proceeding. Here we see a graph of reactant and product concentrations as a function of time for that same reaction. We see here that we have H2 plus I2 yielding 2HI, the same reaction we saw earlier, and we're plotting time on the x-axis and concentration on the y-axis. So we see that over an interval of 40 seconds, we can see that the change in the H2 concentration is negative 0.28 molar, but the change in the HI concentration is 0.56 molar. So notice that the HI concentration is increasing twice as fast as the H2 concentration is decreasing, and this is represented in the balanced equation. The average rate of change is measured in changes in concentration over a particular period of time. And just as we saw earlier, we'll see that as in a small linear region of a curve. So the larger the time interval, the more we deviate from linearity, the more the average rate of change deviates from that instantaneous rate. In order to determine the average rate of a reaction, we'll need to measure the concentration of one of the reaction species at definite time intervals. For example, we see here we're measuring the concentration of H2 from the previous reaction at the time interval, which is 10 seconds. So every 10 seconds we get a reading. So at 0 seconds, or our initial concentration of H2 is 1 molar. Then at 10 seconds it's 0.819 molar. At 20 seconds it's 0.670 molar. So as we would expect, our starting material is decreasing as the time increases. So the starting material concentration is decreasing over time. Now we can calculate that change in concentration every 10 seconds by subtracting the, let's say, 0.819 minus 1. We see here the difference. 0.670 minus 0.819. We see here the difference. And so we're changing by a certain amount every 10 seconds. And that's how we can measure the rate of change over that interval. As our time interval becomes smaller and smaller, what we're measuring is the instantaneous rate of change in concentration at a particular time. And this is our slope at that point on the curve. The instantaneous rate is determined by taking the slope of a tangent line to the curve at that particular point. So, if you've had calculus, this would be the first derivative of the function. So if we're plotting time versus concentration, we'll plot concentration on the y-axis and time on the x-axis. We'll see that our product increases as our reactant decreases. And at some point, the concentration of each species levels off because the system either reaches equilibrium or we run out of reactants. We have to consider the balanced equation when we are calculating the rate of the reaction. And so because the coefficients aren't always the same in a reaction, and because we're losing starting materials and gaining products, we can express the rate in terms of any one of the species in the reaction, but we have to consider the coefficients of those species. So the rate could be expressed as negative 1 over the concentration of, say, A, and its change over time, minus negative 1 over the concentration of, say, B and its change over time. And these would be our reactants. So if H2 is A and I2 is B, and let's say HI is C, right? Then negative 1 over 1 dA dt, or change in A over time, is equal to negative 1 over 1 dB dt for I2, right? Its change over time is equal to positive for the products 1 over, this would be 2 for HI change over time, right? So we write negative in front of the starting materials and 1 over the coefficient and their changing concentration over time. And we write positive in front of the products, 1 over the coefficient and their changing concentration over time. Let's revisit the graph that we saw earlier for our reaction. H2 plus I2 yields 2HI. We can express the rate in terms of, for example, the H2, which is one of our starting materials. We see that H2 changes by negative 0.28 molar over 40 seconds. So we can express the rate as, remember, negative in front of the starting materials, negative 0.28 molar divided by the time interval, which is 40 seconds, gives us a rate of 0.0070 molar per second. Now, we can also express the rate in terms of our product, HI, but we see that the coefficient for HI is 2. And since it's a product, we don't put a negative in front, we have a positive, so we can express the rate as 1/2 times 0.56 molar over 40 seconds. So, because we have the coefficient 2 in front, this 1 over 2, this 1/2 in front, that gives us the same rate for our reaction. So by putting the coefficients in front and by putting a negative for our starting material and a positive for our product, we're expressing the rate the same way. So we get the same rate whether we use a starting material or a product.